In this episode of Cosmos, we embark on a journey to our star to unravel its origin and physical characteristics. Learn about its chemical composition, axial rotation, and glorious luminosity. Delve into the Sun's internal structure and reveal the complexity of its atmosphere. Explore the intricate mechanisms behind the creation of stellar light and discover the nature of the solar wind. Unveil the secrets of enigmatic phenomena like sunspots, solar prominences, chromospheric flares, and coronal mass ejections. Witness the extraordinary space missions that have ventured to study the nearest star in the universe. Sit back, relax, and enjoy the show. The Sun, the brightest object in the sky that makes life on Earth possible. Ancient civilizations worshipped it as a supreme deity and built monuments to measure its apparent motion. The Sun is a giant plasma sphere in the center of mass of all bodies in the solar system. That point, called barycenter, is usually located within the body of our star. Its position is affected by the spatial configuration of the giant planets. Occasionally, the barycenter is displaced in the solar atmosphere. The Sun is about 150 million kilometers away from the Earth. By convention, that distance is equal to 1 astronomical unit. Once emitted, sunlight takes 8.3 minutes to reach our planet. The Sun is a medium-sized star in the prime phase of its life cycle. It is more massive than 75% of the stars in our galaxy, which numbers several hundred billion. The Sun was born around 4.6 billion years ago from the gravitational collapse of an interstellar gas cloud. The gas cloud consisted of cold molecular hydrogen and had a size of about 1 light-year. 1 light-year is the distance light travels in 1 year, equal to 9.46 trillion kilometers. The collapse was initiated by pressure waves from the explosions of nearby massive stars. That process enriched the concentration of gas and dust. After several million years, a protostar formed at the center of the cloud. The primordial cloud had a certain angular momentum that increased during the collapse. As a result, a disk formed in the equatorial plane of the central body. Due to gravity, the proto-sun continued to accrete material from the disk. The lack of transparency led to a significant rise in temperature. When the temperature in the core reached 14 million degrees Celsius, fusion reactions began. The reactions caused a powerful radiation pressure. Radiation prevented further collapse and marked the birth of our star. The physical characteristics of the Sun are impressive. Its diameter is 1,400,000 kilometers, equal to 109 Earth diameters. Its volume can fit 1,300,000 planets the size of our own. The mass of the Sun is 330,000 times that of Earth and 1,000 times that of Jupiter. As unbelievable as it may sound, our star contains 99.86% of the solar system's mass. The mean density of the Sun is relatively low, about 1/4 of Earth's density. The Sun rotates on its axis counterclockwise, like most bodies in our system. Such rotation is called direct motion. The Sun and the Solar System inherited their rotational direction from the primordial gas cloud. Our star does not rotate as a solid body. Each heliographic latitude has a different surface velocity. The equatorial region moves faster and completes one rotation in 25 days. The rotation period increases with latitude reaching 33 days at the poles. The Sun has a higher luminosity than 85% of the stars in our galaxy. Its surface temperature is about 5,500 degrees Celsius. Based on its spectrum and mass, the Sun is categorized as a yellow dwarf star. Stars approximate the idealized concept of a black body in thermodynamic equilibrium. A black body does not reflect light. Instead, it absorbs radiation across the entire electromagnetic spectrum. A black body, with the temperature of the Sun, emits most of its light at a wavelength of around 500 nanometers, corresponding to a green-yellow color. The mass ratio of the Sun consists of about 74% hydrogen, 24% helium, and 1% heavier elements. In astronomy, chemical elements with atomic numbers higher than helium are deemed metals. Their abundance in a star determines a characteristic called metallicity. The Sun has a high metallicity because it belongs to the latest generation of stars in the universe. There are 3 stellar generations in reverse chronological order. Our star is part of population 1. All the heavy elements found in the Sun were created by stars from previous populations. Most of the substance in stars is in the form of plasma. Plasma is a state of matter with a very high temperature. Neutral atoms undergo a process of ionization and break down into ions and electrons. The structure of the Sun has 2 main components, a body and an atmosphere. Each of them consists of several layers with different characteristics. The body comprises a core, a radiation zone, a convection zone, and a photosphere. The Sun's core spans 1/4 of its radius and has a temperature of about 15 million degrees Celsius. That temperature results from the thermonuclear reactions in the center of the star. They fuse hydrogen nuclei into helium nuclei, releasing an enormous amount of energy. Every second, the Sun converts 5 million tons of matter into energy. The process is in a self-sustained equilibrium. As radiative pressure increases, the rate of nuclear fusion slows down. With decreasing temperature, gravitational contraction takes over, and the fusion rate accelerates again. The released energy is in the form of powerful gamma radiation. If you are enjoying this video, give it a thumbs up and share it with your friends. Subscribe to the channel and hit the bell button to be notified of new episodes. You're welcome to post questions, thoughts, and recommendations in the comment section below. If you value our work and like to support it, please consider donating and visit our Patreon page. Join us on social media to stay updated with the latest space news and short clips on upcoming topics. Keep watching Cosmos to learn more. Above the core lies the radiation zone, which occupies 1/2 of the Sun's body. The temperature gradually decreases to about 2 million degrees Celsius at the top of the layer. Gamma rays originating from the core interact with the ionized matter in that region. The plasma absorbs and re-emits them as an increasing number of photons with lower energy. Those interactions continue for hundreds of thousands of years due to the high plasma density. When the photons finally reach the surface, the majority radiate into space as visible light. The radiation region is followed by the convection zone, which extends over the last 1/4 of the Sun's radius. That layer has a much lower temperature and density. Near the surface, the temperature drops to 5,700 degrees Celsius. Energy transfer here occurs not through radiation but by the process of convection. At the base of the region, convection cells of hot matter form and rise toward the surface, where the plasma releases its energy. As it cools down, the plasma sinks again. That convection creates a constant transfer of heat. It is also responsible for the formation of the solar magnetic field. Due to the sun's axial rotation, the convection cells swirl, and the electrons and ions within them generate magnetic field lines. The photosphere is the visible surface of the sun. It is the outermost layer of the solar body and has a width of about 500 kilometers. The temperature of the photosphere is approximately 5,500 degrees Celsius. Its density is 6,000 times lower than the density of Earth's atmosphere. Solar light emanates from the surface, then passes freely through the transparent atmosphere. The upper part of the photosphere is slightly cooler than the rest of the layer. That makes the visible edge of the solar disk appear dimmer relative to its center. Viewed up close, the surface of the sun is granular, resembling boiling thick liquid. It consists of individual cells with sizes between 1,000 and 1,500 kilometers. They have a lifespan of about 20 minutes. The cells result from rising convection flows and thus have a bright center. The periphery of the cells has a dark boundary where cooled plasma descends. Plasma spicules, as long as 10,000 kilometers, stretch above the granules. They are responsible for the apparent irregularity of the solar disk. The sun's atmosphere begins after the photosphere. It consists of a chromosphere, a corona, and a heliosphere. The chromosphere is the bottom layer, with a width of 2,000 kilometers. During a total solar eclipse, it becomes visible as a red ring surrounding the dark lunar disk. The temperature at the base of the chromosphere is about 3,800 degrees Celsius, but near the corona starts to increase. The solar corona is the hottest atmospheric layer. It extends up to 15 million kilometers. The corona has a non-homogeneous structure with more luminous radial rays. Its plasma density decreases with altitude, and its temperature rises sharply. 1.4 million kilometers away from the sun's body, the temperature reaches 2 million degrees Celsius. It is due to chromospheric flares ejecting hot material into the corona. Even further, the corona becomes sparse and cooler and transitions into a heliosphere. The heliosphere is the largest structure in the solar system. It extends to a distance of about 100 astronomical units. Beyond lies the heliopause, a boundary with the interstellar medium. The heliosphere is a continuation of the corona in which plasma expands in the form of solar wind. The plasma drags the solar magnetic field out from the corona, shaping an interplanetary magnetosphere. The solar wind propagates in a spiral pattern. It contains protons, electrons, and a small amount of heavier nuclei. The particles have enough kinetic energy to overcome the sun's gravitational pull. Near Earth orbit, the solar wind velocity exceeds 400 kilometers per second. Its density is about 10 particles per cubic centimeter. The characteristics of the solar wind are directly related to our star's activity. Solar activity refers to various dynamic phenomena in the photosphere and the corona. Global and local changes in the magnetic field are responsible for the emergence of those phenomena. One manifestation of solar activity is the sunspots, darker areas on the sun's surface. They range in size from a few thousand to tens of thousands of kilometers. The central region of the spots is about 1,200 degrees Celsius colder than its surroundings. Sunspots form due to powerful magnetic fields that prevent the rising flow of hot plasma. Local magnetic fields have a random, chaotic distribution. Sunspots are short-lived but usually appear in groups, remaining visible for months. Every 11 years, we observe an absence of sunspots, called solar minimum. It coincides with a change in the polarity of the global magnetic field. In the middle of the cycle, there is a solar maximum with a peak in the number of sunspots. The most beautiful phenomenon in the atmosphere is the solar prominences. They form arcs containing plasma from the chromosphere. Prominences arise between two sunspots with different polarities. They are colder than the surrounding corona but are 100 times denser, making them exceptionally bright. Solar prominences can exist for months and extend for thousands of kilometers. The biggest one observed so far has a length of over 800,000 kilometers. Solar flares are an explosive manifestation of the solar activity. They cause a brief surge in solar radiation across the entire electromagnetic spectrum. The eruptions usually occur in regions with sunspots. Flares lead to a localized increase in the brightness of the solar disk. When magnetic field lines interact, they release enormous amounts of energy and eject plasma into the corona. Thus, the concentration of high-energy particles in the solar wind rises. Solar flares can last from minutes to hours. They are responsible for geomagnetic storms and polar auroras on Earth. Coronal mass ejections, or CMEs, expel large amounts of plasma into the heliosphere. They are a consequence of powerful solar flares. Usually, the ejection is preceded by the appearance of big prominences. During a CME, a vast plasma bubble forms and maintains its structure to several solar radii. Those events can occur up to 2 or 3 times a day. Depending on their direction, they may reach our planet. The most powerful CMEs pose a risk to humanity because they are capable of disrupting power grids and communication systems. Therefore, a fleet of spacecraft monitors the sun's activity. Space exploration of our star began in the 1960s with probes from the Pioneer project. In the next 50 years, NASA, JAXA, and the European Space Agency carried out multiple missions. A notable one is the Parker Solar Probe, launched in 2018. It is the only spacecraft to reach the solar corona and is still operating today. Its main objectives are the study of energy transfer in the star and the solar wind. The most recent mission to the Sun is called Solar Orbiter and began science operations in 2021. It will investigate solar wind's impact on the space environment in our system. The Sun is the only star in the entire universe that we are able to study up close. The knowledge learned expands our understanding of the solar system and its evolution. Monitoring of solar activity is vital not only for the future of humanity but also for our prospects in the near cosmos.